Hello, everyone. I know we have people from all around the world, so good morning, good afternoon, evening, night, from wherever you are. My name is Csaba Fitzl, and I will talk about how to mitigate exploits using Apple's Endpoint Security framework. So a few words about myself. I work as a content developer at Offensive Security. I used to be a red and blue teamer at a large company for about 8 years. Recently, in the past 2 years, I started to do macOS security research. I have a wife, 2 kids, and I love to do hiking and also yoga. So what I will talk about, it will be a very condensed talk, so I have a lot to cover. I will start with going over briefly about process injection and signaling attacks, basically the attacks that drove me to write the application I will talk about. Then I will cover the endpoint security framework very briefly. Then I will talk about the application called Shield that I developed to protect against exploits. I will talk about the application's logic, how it works, and finally I will show a demo. So process injection attacks. Process injection in general is a very known attack or technique on all of the OS platforms, but on macOS it's very unique, and it's very strictly forbidden to do. And it's because the macOS security model is very closely tied to code signatures and entitlements, which are inside the code signatures. Because these entitlements give processes and applications more rights than they would have. If you can inject a code into a process, you can impersonate that process and gain access to its entitlements. Because of this process injection is really restricted on macOS. For example, if we can impersonate a process, we can access maybe privacy-related settings. If that application is authorized to access maybe our microphone or documents, we can access the keychain. We can maybe impersonate an XPC client and escalate our privileges, and so on. There are several techniques on macOS to perform injection. Probably the most classic and known one is using the DYID insert library's environment variable. Basically, here we can specify a dylib and start our application, and then our dylib will be injected into the application, and it will actually run before the application even starts. These days on macOS with system integrity protection, this doesn't really work for platform binaries, and if your application is signed with hardened runtime, then SIP will protect your application. So this cannot be used unless we use an entitlement to specifically allow this type of injection. But if possible, we shouldn't use this entitlement. The next big chunk of process injection is dylib hijacking and proxying. This was discussed really detailed by Patrick Vardell back in 2015. The base idea here is that we plant a dylib that the application is looking for, and the application will load our dylib. We can also replace a dylib inside the application, and in that case, it's called dylib proxying attack. But the idea is that the application will load our dylib. Now, since we have system integrity protection, the same rules apply. It will be not allowed. Also, if the application is compiled with library validation, it will be also not allowed unless the dylib is signed with the same developer certificate. Of course, there is an entitlement to enable it, and it's really dangerous to do so, and it actually led to plenty of exploits and vulnerabilities both on Apple side and third-party side. The main design issue here is that if an application has to support like third-party plugins, drivers, then that application basically have to use this entitlement, and it will open it up for process injection. Task forbid this is an injection that works by getting access to the process task port, and if we can gain access to the task port, basically we can do anything with the application. We can read its memory, write its memory, create a new thread, really whatever we want. Again, system integrity protection will protect against such attacks, but there is the COM-Apple security get task allow entitlement, which will open up the application for this type of attacks. And this is needed. This entitlement is needed because when we develop an application and we want to debug the application, we actually attach the debugger using the task port. And because of this, actually Xcode will attach these entitlements to every debug build it creates. And nowadays, notarization will not allow application with these entitlements. But in the past, there were issues that happened because someone released the development build instead of the release build, and this entitlement was present in the application. And the last group of injection I would like to talk about is related specifically to Electron applications. Security people don't like Electron application, especially because their threat model doesn't really consider local attacks, although they started to improve in this space recently, but it's still wide open. We can still use the Electron run as node environment variable to start an Electron application in a Node.js prompt, and then run our custom JavaScript inside that application and thus inject custom code, or we can use the --inspect argument with any Electron application, basically starting it in a debug mode, and that will also allow us to inject any code into the application. And this is not good. And all of these injections led to various vulnerabilities, a couple of local privilege escalation attacks related to XPC. This was possible because I could inject code into the XPC client and basically reach XPC services that I shouldn't have access to. And also it led to various TCC bypasses. And these CVs or vulnerabilities, just a few to name. The next group of attacks are the symlink or file link based attacks. The approach is very basic in this case. The issue is typically is that there is a process running with high privilege, typically root, and it will write or modify files in a user controllable location. And in those cases, what a user can do, he can delete that file and replace it with a symlink or a hard link, point that link to a location which is only available for root, and potentially achieve something. In a very base case, it will be an arbitrary file overwrite issue, or maybe a file deletion issue, but in some cases it can lead to privilege escalation. And again, a couple of vulnerabilities related to file link attacks, both in macOS and Adobe. And again, this is just a couple of the ones I found, but there are many more. And because of all of these issues, I wanted to do something about them and find a way to mitigate all of these attacks in their core base. So basically mitigate the exploits generically, not just these specific issues. And then I turned to the endpoint security framework, and I found that I can use that to mitigate all of these attacks, basically. But before I talk about the application, the endpoint security framework, I have to talk about the mandatory access control framework. The Mac framework has origin from trusted BSD, and then it was adopted by OS X. It's a policy framework implemented inside the kernel, and it allows basically policy plugins or modules to be installed inside the kernel. And the kernel has several hooks implemented typically in the system calls. And those system calls call out to the Mac policy modules to make a decision if that action is allowed or not. And this is a really, really powerful framework because there are over 200 hooks in the system calls. So it allows a really granular control over basically every action. And we can install multiple modules, and Apple itself uses these modules, like Sandbox uses the Mac framework, the Apple Mobile File Integrity uses this framework, and also Endpoint Security uses this framework to monitor actions. Now, this framework was never officially supported by Apple, but it was part of the kernel development kit till OS 10.12, and then they removed the Mac header at that point. We can still get the Mac header from the XNU source code, but again, it's not an officially supported thing. So just to give you a brief overview how the Mac hooks happen in the kernel side. So I picked the snapshot mount system call, which can mount an APFS snapshot. And it has a function call called Mac mount check snapshot mount. And basically, this is a call out to the Mac policy modules. And this function will do a couple of checks, and ultimately it will call the Mac check macro or function with the mount check snapshot mount argument, which is specifying the name of the hook to look for. And then comes Mac check, which is basically doing the callouts to the various policy modules. So what it will do, it will iterate over all of the installed policy modules, and it will check if that module implements this hook or not. If yes, it will call it, get the results, and move on and call the same hook from the other modules as well, and aggregate the decision. Basically, if any of the modules denies the action, then the action will be denied. If everyone permits, then it will be permitted. Again, there are over 200 of these hooks, so it's a really, really good framework for security. So let's move on to endpoint security. Again, this is a huge topic in itself. Scott Knight gave an excellent talk at Objective by the Sea, I believe 2 years ago. I highly recommend watching it. He also have a blog post about it, and actually this image is from him. The endpoint security framework has quite a few components. It has a kernel extension, the endpoint security kext, and it's tightly integrated with the Mac framework, the out framework, the K-out framework, and also with audit. It will implement a lot of hooks in the Mac policy module. Then we have the lib endpoint security dilib, which is implementing all of the C APIs that we can use in our endpoint security client. Then we have the endpoint security daemon, which is responsible for loading our system extension through launchd. There is the sysxd daemon, which is responsible for validation and validating the system extension and copy it to its final place, because it's being staged similarly to kernel extension. So it will be moved into library system extensions. And then finally, we have the system extension framework, which we can use from our main application to activate or deactivate the extension. And there is a CLI tool, the system extension CTL, which allows some basic control of sysxd to load, remove some of the system extensions. Now, let's go back to the Mac framework with Endpoint Security. This is a screenshot from IDA Pro. We can see that at this point, Endpoint Security implements around 60 hooks in the Mac framework. So it's really granular. So we can see there are hooks for files, IO kit opening, kex loading, mounting, the get task, and so on and so on. So there are a lot of hooks, and these allow really granular inspection of the activities going on. And on a high level, what happens, and it's not 100% true, because there is also the K-out framework and audit, but on a very high level, there is a correlation between the endpoint security events we can subscribe to with our endpoint security client, and between the Mac policy hooks. So basically, just here are a couple of examples. The ES event type notify chroot event, we get it when chroot is being used. It's related to the ESVNode check chroot Mac policy hook. The mmap event is related to the mmap policy hook in the endpoint security Mac framework. And so on. And this mapping, or this idea, makes the framework really powerful, because essentially you get a user mode extension of the Mac framework from kernel mode in user mode. And considering that the Mac framework was never officially supported for third parties, it's heavily used by Apple, but it wasn't supported for third parties. Now we get it in user mode to some extent, and I think it's great. So I wish we would have something similar in Windows as well. So with that, let's talk about the application I developed for protecting against these exploits. Now, when we develop an endpoint security application, there is one very hard requirement, and is having access to the COM Apple Developer Endpoint Security Client entitlement. This is not available for everyone who has a developer ID. You need to request this from Apple, just like we had to request a kernel code signing certificate in the past. And it wasn't always granted. And unfortunately, this is Apple's goodwill, and this is my pain point in this entire process, because it's really hard to get this entitlement. I asked for it back in March last year. Then in April, I got the developer version. I think this step goes usually easy. Everyone gets it. We can use the developer version to install our application on our own Mac without the need of turning off system integrity protection, but we cannot use it for distribution. And I started to ask for the distribution version, and I started to send emails that, hey, what goes on? I would like to have it. And it felt like all those emails are going into a black hole. I never got a reply. I got a reply in June or July with one question. I answered it, and then again, silence. Nothing happened till this year, January, when out of nowhere, I got the entitlement. And I think this process is super frustrating, annoying. I find it a really bad developer experience. And it's also very demotivating. Like, I stopped developing this application last summer and picked it up again this year because I just didn't see any point doing that. And I don't do this for a living. So I'm not a developer. I'm usually looking for vulnerabilities as a hobby, writing trainings as my main job. So I'm not developing application. I'm not selling application. This application is open source and free. So I don't depend on this entitlement at all. But I think if someone depends on it and does development for a living, then it's even worse experience. So if you need it and have plans to develop a security application, then be sure to request it early. And you also need to start writing the application, because as I understand, you kind of need to show Apple that you have intentions using the entitlements. But with that, as sources like source code, I heavily used Patrick Wardlow's Process Monitor and File Monitor application, and actually I took some source code snippets directly from his code base, and it helped a lot to understand how endpoint security works and how should I write an application in that. And I also used Stephen Davis' Crescendo application, which is also open source, and it's written in Swift. So just quickly, how do we write an endpoint security client which goes into the system extension? It's not a difficult process. I think it's fairly easy. First, we define an endpoint client as an ES client T type. We create an array with all the events we are interested in. And then we create a new client with the ES new client function, where we specify our client variable, and also a block which will be invoked whenever there is an event coming. And then inside that block, we can handle the events. There are notification events and there are authorization events, so we can deny an action. And at the very end, we call ES subscribe, with which we can subscribe to the endpoint security events. And basically, that's it on a very high level. This is what we need to do. And then how the application is working, how I use this framework to mitigate all of the exploits or the process injection and the filing attacks I talked at the very beginning, because I found that all of them can be prevented actually in a very simple way. So the first event I'm interested in is the ES event type out_exec. This is invoked every time there is a new process starting up. And I check a couple of things. First, I check its arguments. If it has any of the Electron debug arguments like inspect break, and so on. And if any of those present, then it will be either detected or logged, or it will be denied if the application is configured to deny an action. And then I also check for 4 different environment variables which allow code injection. And if any of those present, I can just deny the application from starting up. The next event is the ES event type out_get_task, which is basically invokes whenever someone wants to get the task port of an application. This is simply denied or detected. So it's a yes and no. So there are no further checks. In an under normal circumstances, there is no reason an application should get another application's dark spot unless you do debugging and the application supports an LO list functionality, so you can put LLDB or Xcode on that, and then it will work. But then it can stop the rest of the attacks. Then the next event is the out mmap. This is invoked when there is an mmap event happening. So when someone maps a file into the process virtual address space. I use this to monitor for dilib injection. It's not perfect, but this is the best I can do right now. And I even talked to Apple, and they also didn't have any better solution right now. So basically what I try to do here is whenever a dilib is loaded, I kind of try to enforce library validation. So I will check the signature of the dilib being loaded and compare it with the signature of the process loading the dilib. And if the team ID doesn't match, then it will be detected as a dilib injection. Now, the problem here is that I actually need to read the dilib from disk, which is slow. So if there is a large application starting up, this can hold up the application for a couple of seconds because of the disk I/O. But there is no better way. Apple has the luxury to do library validation in kernel space in memory during runtime, which is 1,000 times faster. But we cannot do the same with this framework. So this is the closest I could get. The next event is the outlink event, which is being invoked when there is a hard link creation. The check is really simple. A low privilege process shouldn't create a hard link pointing to a high privilege location. If it's happening, then it's a potential exploitation. If it's happening actually the other way around, so if a high privilege application is making a link pointing to a low privilege location, then it's a vulnerability, but it's not being checked by the application. And finally, the notify create event, which is being invoked whenever there is a file creation. This is what I use to check the creation of symbolic links. Unfortunately, here I cannot use the authorization event, because if the symbolic link is not yet created, I don't know its destination. So I can only check after it's being created. So this is a detection only, but the logic is the same. A low privilege process shouldn't create a symlink pointing to a high privilege location, but it works. And I have a demo with an XPC exploit. In this XPC exploit, I had to inject code into a client application, which in this case was the ClamXev AV. And with XPC, basically, with the exploit, we could create a plist file inside launch daemons, which is basically a privilege escalation to root. So we use the dwyld insert libraries for injection. And now after the injection done and the exploit run, we can see that there is a new plist inside launch daemons. And again, this was possible not just because of the XPC vulnerability, but because we could inject code into the client. And let's see what happens when we have the application running. So again, I will try the injection, and then we get a notification that it was blocked. And if we check the launch daemons again, the plist is not there. So basically, the exploit was prevented generically, which I think it's pretty good. So to summarize what I talk about, process injection and filing attacks are responsible for many logic bugs on macOS, in third-party applications and macOS itself. And we can use the endpoint security framework and its events to track these in a generic way and prevent these filing attacks or process injections. And this is all possible because the framework is based on the Mac framework in the kernel mode. And the tight integration of these two makes it a really powerful framework for security products. And yes, it's really hard to get the entitlement if someone would like to develop such an application. Thank you for listening. I will be at the Discord channel for Q&A, and you can also find me on Twitter running by the Evil Bit.